Welcome to the cutting edge stage at CogX 2021. I'm your MC, Jess Wade, a research fellow at Imperial College London. Many thanks to Accenture, BT, Visa and Quantum Black for supporting CogX, and to you all for making it along to our hybrid festival. Over the next 2 days, we have some extraordinary speakers, presenters and discussions introducing us to all things cutting edge in technology. So what exactly does hybrid mean? Well, for this festival of all things tech, hybrid means that we have some sessions that are running fully virtually and some sessions that are fully in person and some sessions that are hybrid, a mixture of the two, with some physically in person in our live space in King's Cross and some connecting in from around the world. Think last week's G7 summit, but with more facts and innovation and less images of Cornish beaches. If you're connecting from somewhere around the world, it's worth remembering that the UK are experiencing a heat wave and we're not a country that has fully invested in air conditioning. I should also mention that we have a code of conduct, which you can see on the CogX website, that explains the behavior that is and isn't appropriate in this event and other events that are going on throughout the course of the festival. Throughout the next few days, I encourage you to tweet and share your experiences on social media. There is a hashtag, it's hashtag CogX2021. Hopefully you can see some exciting stuff there already. And if you have any questions for our speakers, please submit them using the Q&A function and we'll come back to those at the end of the discussion. Today, we have an absolutely incredible lineup. From neurorights to AI policy, quantum sensing, and even spatial computing, we're bringing ideas straight out of the lab and direct to your laptop. And the wonder of the hybrid conference means that you can get comfortable, do the washing up, take the conference on your headphones while you're going for a socially distanced walk. Having said that, for the first session, we're going to have slides, so please try and stay close to your laptop if at all possible. Our first session is led by the physics master, Helen Czerski, who's going to take us on a journey through the physical world. Our tech may advance, but the fundamental rules for living on the planet stay the same. And they've been running things on Earth for billions and billions of years. What can we learn from this perspective when it comes to the technology that we create, and how do we use it? Helen Czerski is a physicist, an oceanographer, a broadcaster, and a writer. She is currently based at University College London. Okay, over to you, Helen.
Thanks for the introduction, Jess. I'm going to share my screen so everyone can see what I've got to show. So here we go. So I recognize that it's a bit of a strange thing to start a tech session with a physicist guide to life on Earth, but there is a reason for doing this. And it's partly because we have a very specific idea when we think of physics quite often, which doesn't encompass all of physics. And the other thing is that we live on a world that does have constraints, and that's not a bad thing. We all know that constraints stimulate creativity, all that kind of thing. And we need to know what our constraints are. So I'm going to be talking a little bit about the physics of the planet, a little bit about my research in uncovering the physics of the ocean, but also the important things about perspective, like what can physics show us about how to look at our planet. So I think each of us has 3 life support systems. We have our own body, we have planet Earth, and we have the infrastructure of our civilization. And those 3 are all needed to keep us alive. They mostly work separately, but you can see that there are problems when they come into conflict with each other. That's why climate change is a problem. It's the infrastructure of our civilization, our civilization life support system butting up against the life support system of our planet. And if 2 life support systems come into conflict, you're going to have a problem because they both matter. It's not easy to prioritize one over the other. So this framing of these life support systems, I think, is really valuable in how to look at problems in the world and how to look at what motivates us to do things. I'm a physicist, I study the ocean. That means I study the planetary life support system. But of course, you can't do that now without considering how it interacts with the other 2. So this is all about a physics perspective on a planet. And physics, there are many ways of defining it, but I think of it as the study of energy and matter. That's the framing. It's not separate to chemistry or biology. It's just, this is the framework for looking at what we call physics. And it is the study of energy and matter. So to start off with, I want to take a brief tour through the big picture of how energy and matter, how that manifests itself on our planet. So let's take a look at the energy first. We know energy comes from the sun. The bit that people talk about a bit less is that energy is then re-radiated into space. So what that means is that sunlight hits the Earth, some of it's reflected immediately back out into space, some of it is taken up perhaps as heat in the oceans, or it's taken up by photosynthesis. It moves into the engine of the Earth, but it doesn't just keep accumulating there, because otherwise our planet would just get hotter and hotter and hotter. So after some time, that low-level heat energy is re-radiated away into space. So Earth is basically sitting in the middle of a waterfall, if you like. Energy flows in from the sun, it hangs around for a bit, and then it flows away again into space. And that's all well and good, except that there's a problem with the numbers at the moment because of humans. So here are the numbers. On average, the Earth receives, on average over a year, 343 watts per square meter of energy from the sun. And the problem that we have created is that putting all this carbon dioxide into the atmosphere has slowed down the rate at which energy leaves. And that means the rate at which energy is leaving is only 342.5-ish watts per square meter. It depends a little bit. And making a very precise measurement is a little bit tricky. But the point is, slightly less is going out. And so there is an imbalance. And that means every year the Earth gains a little bit of extra energy because it hasn't lost it. So about 0.1% of the energy we get every year, we're now holding on to, and that is sloshing around the Earth system. And we know where it's going. 90% of it is ending up in the oceans. That's a whole other talk. But the image I want to put in your head is this image of an energy waterfall with energy flowing in, energy flowing out, but it hangs around in the system while it's on Earth. And that's the important bit for us, because that's what runs the planetary engine. And the reason that this extra heat energy matters is if you add extra energy to a system, the engine will run slightly differently. And that's why climate change is a problem. It's because it changes what's in the engine. So what am I talking about when I'm talking about the engine here? An Earth scientist would consider there are 5 major systems: the atmosphere, the oceans, life, rocks, and the ice. And they're traditionally studied separately, but of course they interlink. So when I talk about energy flowing into the system, it's held in these reservoirs. It does things move as a consequence of the energy that's inside them. And so the engine turns, right? You know, heat flows perhaps from, sunlight perhaps heats up the land, and that moves into heat energy that warms air, that causes winds, so you have kinetic energy that eventually gets dumped into the ocean, so it turns back to heat energy. So that the Earth is this gigantic spherical engine that is running off the energy that is flowing through it from the sun. That is what we live on. That's what planet Earth is. And of course, we can tap into some of this energy whenever we use renewable energy. We're tapping into that massive energy flow through the planet. So the story for energy, the big picture physics story for planet Earth, is that energy passes through the system. And then I said the other thing that mattered was matter. Well, let's have a look at what Earth does to matter. So to illustrate this, I want to go back to London in the 1850s. And London was a mixed place, I think we can say, in the 1850s. It was a big city. It was the center of what was then, beginning to be an empire. And it was full of muck and dirt, and no one had a good way for getting rid of it. So most of it ended up in the River Thames, which is the big river that runs right through the center of London. It's the reason that London exists. But the muck ending up in the Thames was, as the population of London increased, it was getting bigger and bigger and bigger. And so this cartoon that I'm showing here was published in 1855, and it's basically showing a corpse. There's lots of nasty dead things floating. And Michael the scientist at the Royal Institution who did lots of work on magnetism and electricity, he said he's near the bridges, the feculence rolled up in clouds so dense they were visible at the surface, even in water of this kind. And he says the whole river was for the time a real sewer. So basically, civilization was producing a lot of waste, and it was all just piling up in the River Thames. There wasn't enough water flow to take it away. But after a lot of haggling over who was going to pay for the solution, there was a solution, and it came after a summer of the Great Stink, where the stench of the river was so bad it stopped the parliamentarians sitting, and so they coughed up basically for the solution. And here was the guy who engineered it, Joseph Basil Jet, who was a civil engineer. And there's a picture here of what he built. So if you visit London and you stand on any of the embankments, you are standing on Basil Jet's construction. And it was actually the tube ran through it, but mostly what ran through it, the important bit, was two massive sewers that were going to take London's effluence and take it away. And so Basil Jet built this massive sewer system all over London, and it was brilliant at taking all the muck and the poo and everything else away. It made an enormous difference to public health in London. People were dying of disease in their thousands, and this system stopped them. No one is denying the achievement of Basil Jet. However, in retrospect, we can see there's a problem with this, because although it was very good at taking stuff away, nobody ever asked where away was. And where away was the river, the ocean. It didn't go away. It just went somewhere else in the system. So this is how humans have traditionally dealt with what comes out of their civilization. They send it away, and away just means where they can't see it. So that's how humans do it. Let's look at how the planet does it. The stuff, because what I'm talking about when I'm talking about stuff is anything basically, anything that's, the stuff that makes up us, the stuff that makes up the things we pick up every day, any of that material, that's what we're talking about. So the traditional human view has just been to send it away, and it can pile up there, somebody else's problem. Let's look at how the ocean does that, just because the ocean is what I work on. We get ecosystems in the ocean. We get phytoplankton at the top that feed little zooplankton, little animals, and those get eaten by other things, eaten by fish. Things might fall down to the bottom and die. They get eaten by microbes. The point about this system is that everything is recycled, even the poo. We can look at what happens to the feces. We're going to use a whale as an example here. So whales are very interesting because they feed at depth. But when they come up to the surface to breathe, that's when they get rid of their waste material. And it floats. So if you've ever wondered, so whales are actually transporting nutrients, matter from the depths up into the surface of the ocean, and then it can fall down and the whole cycle goes around again. If you've ever wondered what whale poo looks like, it looks like this, although this is a relatively constipated whale. It's usually a bit more liquid. But the point is that what the whales are doing is they're acting as part of a recycling system. They're packaging up material from underneath, they're bringing it back to the top of the ocean where it can get remade into new materials, into new animals. And that's the way the planet deals with its matter. It's basically all about recycling. We live on a planet that only has so many atoms. We've only got so much cobalt, we've only got so much lithium, we've only got so much nitrogen, and it's all going round and round. So these are the fundamental physical principles on which our planet operates. The energy is passing through in this waterfall model. It gets siphoned off along the way to run the engine, but fundamentally, most of it is ending up back in space, apart from the bit that we're accumulating at the moment. And the matter in the system, it just goes round and round. There is nowhere else. There is, for all people talk about mining asteroids, it's not a significant source of any mineral. Compared with what we already have on Earth. So what we've got is what we've got. We're living on this little island, and these are all the atoms we've got. We've got lots of them, but they are all we've got. So that's the really big physics picture. Now let's look at how we define physics. So I'm a physicist, so I hope you don't mind the graph. It's not a very serious graph. We've got time on the bottom and size at the side. Now physics has there's this sort of, popular myth, if you like, that physics comes in two species. There's cosmology, which is very big, very slow things out in the universe. And there's quantum mechanics, which is very small, very quick things that happen far too fast for us to see. And this is the view of physics. It's those two things, but that is not true. And it's not true because it's not true that that's all there is. And the reason it's not true is because of all the stuff in the middle, all of these things, coffee stains and toast and wind turbines and planets and volcanoes and bubbles. All of these things sit on the size and time scales. They sit in the middle. They do not need general relativity to explain them. They don't need quantum mechanics. Classical physics is totally fine. But if we adjust this scale now, we can see we've got quantum things that are very, very small, cosmological things that are very, very big. And then there's all this stuff in the middle. And here's the thing, is that people think of there being, two, so the big aim of physics is to unite cosmology and quantum mechanics, because if you make things complicated enough, like in the middle of a black hole, the cosmology and the quantum mechanics kind of join up around the back. But all this stuff in the middle, that's the place where life gets interesting. That's the place where the laws of physics interact in really complex ways to make our world. And this is the frontier of physics that I think really matters. It's how we deal with complex systems. Because this is what we live in. We are part of a complex system. The fact that a human can even exist is a very complex thing. So we need those complex systems. So this middle frontier, this is the physics that really matters in our everyday life. So how do we get into that kind of physics? And actually, both the cosmologists and the quantum mechanics people will freely admit that this physics in here is far harder than anything at either end, because complexity is hard. So I want to shift to giving you an example of how a complex physical system and the physics of that system matters for our planet. And this is my area of research. So we have this engine, this wonderful spherical engine that is our life support system, our planet, and it's got reservoirs on it. And there's two massive reservoirs that are relevant for what I'm about to say. One of them is the atmosphere and one of them is the ocean. They're big pools of stuff. And stuff can move between those two reservoirs, but it doesn't move easily. So the surface of the ocean, which is what I study, is the gatekeeper for what goes from one massive reservoir to the other. So let's look at what's in those reservoirs. The ocean holds more carbon than the atmosphere by a factor of about 50. So most of the carbon in the system, the whole planetary system, is actually in the ocean. We have to worry about the amounts that we're moving across the ocean surface matter, but they are they're the difference between two very big numbers, basically. So stuff is passing between these reservoirs, between the atmosphere and the ocean and back again. And then there's energy. So I talked a little bit about energy. We know that it's actually 93% of the extra energy accumulation in the Earth system is going into the oceans. The oceans are the Earth's heat reservoir. The temperature of the atmosphere actually has nothing to do with anything. It's the temperature of the ocean is what represents the amount of energy in the ocean. And that is increasing with time because that's the reservoir for heat on Earth that can then feed heat into other places, and then other things get warmer as well. But it goes via the ocean. So the question here then is about distribution. It's not enough. These are not well mixed reservoirs. If you put something into the atmosphere, it might mix relatively quickly, perhaps over a few weeks or months. If you put something in the ocean, it doesn't mix. If you think about running a bath, if you have a hot end and you're running the hot tap into one end, even in a bath, the hot end will stay hotter than the cold end for quite a while. So you make the ocean, the ocean's a lot bigger than that. And it just doesn't mix. Things are held at different places in the ocean reservoir, and there's a whole load of physics associated with that. So it doesn't just matter where carbon and energy are, that there are carbon and energy in the ocean. It matters where they are, because that affects whether they can get out and interact with other parts of the system. And all of this is driven by physics. This is a complicated physical system. And just to give you a little picture of how complicated it is, I have a right bee in my bonnet about the ocean. I make no apology for that. It is Earth's dominant feature. But I want to show you what it looks like when the planet breathes. So the map here is a map of the globe, and the colors show the ocean breathing on average over the year 2000. So you can see the yellow and red bits near the equator, they are the ocean breathing out, breathing carbon dioxide out. The pink and the blue bits are the ocean breathing in, taking up carbon dioxide. And there are patterns. The engine is complicated. It's breathing in some places, it's breathing out in others. Overall, the ocean is breathing in carbon dioxide, but it's not happening in the same way everywhere. This is a really complicated system. And I'm going to keep going back to this patterns and complexity, that the basic physical rules are fine, but what we need to understand is how they work in this engine, how energy and matter are flowing around the engine, which is dictated by, the fact that we've got land, which is a weird shape, and that the ocean is different depths in different places, and that water moves. This is how the engine runs. So this is a picture of the ocean breathing. And the reason I show this is because of what I study, which is how breaking waves and bubbles help the ocean breathe. And specifically, I have worked in this area up in the North Atlantic, because this is a very important place for the ocean breathing in. So the reason I'm showing you all of this, by the way, is to show you how complexity works in the Earth system. Because it's easy to say something's complex and it just makes it sound very hard. But I want you to show you how that complexity actually manifests itself. And this is just one example of very, very, very many. So out in the open ocean, a wave breaks. It forms bubbles underneath the surface. Those bubbles are like little packets of the atmosphere being carried down into the ocean. But they may not stay down. Some of them are going to rise back up and give things back to the atmosphere. Some of them are going to move further down and take that gas into the ocean. And of course, because the pressure increases as you go down, that gas gets squeezed into the ocean. And then, of course, the bubbles that rise back to the surface, they form the white horses, the white caps that we see on the ocean surface in big storms, or even just when it's a bit windy. And they spit tiny things up into the atmosphere. And so just one breaking wave has all of this going on. And you look out at a stormy ocean. So that these bubble processes, they happen on scales of, hundreds of microns. So less than a thousandth of less than a millimeter, far less than a millimeter in size. And they happen in seconds. And they produce very, very tiny things. But the outcome of this process, the tiny particles that are spat upwards from the ocean surface and the gas that's taken in, that directly affects an entire planet. So you have this mixing of the scales, these really complicated processes in the small scale that link up to really big processes later on. And this complexity is present all the way along that chain. So this is just an example. It's just a picture of the sort of thing I go out to sea to study. So this is in the middle of the North Atlantic in the autumn. You actually can't see, there's nothing in here for scale because we were the only ship out there, because no one else was crazy enough to be there. The average height of the waves in this image, average, was 10 meters. So what you're looking at is a gigantic disturbance of the ocean surface, with these tiny, tiny processes, the breaking waves and bubbles, generating tiny bubbles that are 10 or 20 centimeters beneath the surface, while the entire surface is moving up and down by 10 or 20 meters. And this is the ocean taking a deep breath. You've got these linked, complex processes, all driven by physics, that are happening on lots of scales. And the system is balanced. That's the important thing, that the way, this is the planetary engine functioning. All of these bits are pretty much in balance with all of the other bits. Just as an aside, if you're curious about how you actually study this in practice, it's really hard. The other sessions that you listen to today will all be about, quantum things and nano things and artificial intelligence. And it's all very tidy and clean. But when it comes to understanding the engine of our planet, this is really messy physics. It's not straightforward to get to. You can't just send out a shiny robot. You have to physically go out in very difficult conditions. This is me in the turquoise jacket on the side of this ship here. You can see the ship's tilted over to one side. And this buoy, this big yellow buoy, had a load of bubble sensing instruments on it. This was my experiment. It went out, it floated in the open ocean for the duration of a storm. It could see into these tiny processes just beneath the surface where you certainly wouldn't want to go as a human, and we got the data back. So the point is that this isn't, there's all this new tech going on, but understanding our own life support system and the planet is still a very raw process. It's not that we can't do it. It's not that we're stupid. It's not that we haven't got enough technology. It's that it's really hard to get to. And you have to be really careful in how you measure these things. So this is how this kind of science progresses. And part of my reason for showing this is that in this session where you're talking about, these very shiny AI, neural network type things, you can't forget that this is also there. This messy physical world is also there. And it's actually driving the system that keeps us alive. So those two things exist in the same world. So there's some big questions that come from, all of these things. I mean, for my research, there are questions about, will the ocean keep taking up carbon? It's actually doing us enormous favor. And actually the same can be said for the energy. So just as an example, on the right-hand side here, I love this plot. It's really clear. On the left, you can see the atmosphere in 1870. You can see how much carbon dioxide was already in the atmosphere. The scale doesn't start at 0. And, we've put some carbon in the atmosphere from coal. We've moved stuff around, right? What we're doing when we burn things is we're moving stuff from one reservoir to another. So we've moved it from the geological reservoir into the atmosphere. So we've shifted stuff around the Earth system. We've added carbon into the atmosphere from coal and oil and gas and cement. We've changed the land use. We've taken away some of that carbon because it's been taken up by the land. We've got a lot left in the atmosphere, but there's that enormous chunk. The ocean has taken up a lot of that carbon. It's moved from the atmospheric reservoir into the ocean. About a third of all the extra carbon dioxide we have put into the atmosphere ends up in the ocean. And it's doing us an enormous favor. We will be way past the Paris climate, levels already, the targets, if it wasn't for this. However, we don't know if it's going to continue to happen. So, we need to ask questions about a lot of questions about reducing our burning of fossil fuels, absolutely, certainly. But we also have to consider whether the Earth system that's already taking away a lot of our carbon dioxide, is it going to continue doing us that favor? We can't just invent new technologies without looking at the engineering of the planet that we already live on and look at what it's already doing to help us out. So the answer to climate change is what I'm saying is this is not, it's not some future, it's not just some sort of shiny tech solution. We have to, the engine of the planet itself is already doing a lot of the work for us. We need to understand what it's doing and make sure we don't stop it at the very, very least. So the question here, when it comes back to the physics of energy and matter, is what's in these reservoirs and how is it distributed? How is it moving around our engine? How is it moving around our life support system? And the answer is always that it's complicated because it's based on very complex processes that are very interdependent on each other. So there's this wonderful balance of what was balanced before we came along approximately. Things, energy and matter are moving around the system constantly. And it is a very complex process. You can't just affect one bit of it and expect it not to affect anything else, which is why most natural scientists are very nervous about geoengineering, because we know how complicated this thing is. We're better just to stop the changes we're making before we make new ones we don't understand. It's the understanding that is critical. So this is a very famous photograph. It was taken from Apollo 17 in 1972. And we forget that, everyone made a fuss about Apollo going to the moon, but they went to the moon and the biggest outcome was that they looked back at Earth and we saw ourselves, we saw our planet. And this is where the next stage of the physics comes along, because it's about how we get things done. If you want to understand the life support system that you're living in, you have to understand that system and you have to understand your environment. So there's another thing about that doing this kind of physics teaches you. When you're doing the kind of physics I was talking about, studying the ocean surface, you're living at sea on a research ship in an isolated entity. You don't have internet really. You sometimes have text-only WhatsApp these days, but you're isolated from the world in your ship. You're a tiny thing in the middle of a massive environment and you are studying what's around you. And that is not a new situation in human history. I could talk for a long time about the Polynesians. Polynesia is the triangle on the planet, the map at the bottom of the page here. They these are the Earth's, they are the true ocean civilization on Earth. They are incredibly technically competent at navigating across huge oceans without using modern seafarer, navigation tools. So they've been doing this for 1,000 years in canoes, like voyaging canoes, like the one at the top. And the point is that these ships, they went out, these boats, they went out across the Pacific, and they were observing their environment. And they thought so this is Hokulea, a very famous Hawaiian ship, which explored sort of rebirth of navigation for modern Hawaiians. And they thought that the difficult thing was the technical stuff. They thought that the hard thing was knowing which way to go and how to read the waves and the wind to understand where they were going. But what they learned was that the technical stuff was only half of the battle, and that the real difficulties were all to do with how you keep a team together. They were all human difficulties. And this is something we still recognize now. We think of modern exploration as being, we're going out to the stars, we've got an international space station, people are talking about going back to the moon and going on to Mars. But if you look at how they choose astronauts now, they don't choose them based on their technical expertise. They choose them more than anything based on their character. Can they work well in a team? Will they muck in? Will they hear and listen to everybody else? Will they respect everybody around them? The human challenge, the sort of thing that you learn about on a research ship that has been, it's the same thing. It's the same microcosm that you're in this tiny little bubble. You have to get on with the people around you. Nothing in the technology matters unless the human side is sorted out first, because otherwise you get mutinies, you get unhappiness, you get wastage, you don't get where you're going, wherever it is that you're going. So it's really striking in the books about Hokulea, this canoe, and about the International Space Station. So if you read Chris Hadfield's An Astronaut's Guide to Life on Earth, for example, there are paragraphs about teamwork in those two books which are almost identical, because the technology moves on, but the human problem needs constant maintenance, and we can't forget it. So there's a Hawaiian saying, just to finish with, there's a Hawaiian saying that a canoe is an island and an island is a canoe. And what they mean by that is that the skills you need to live on a small island in the middle of the ocean are the same as the skills you need to do well to get your canoes across the oceans. You don't just need the technical knowledge, you need the teamwork. And of course, it's very easy. I find it very easy to extend this to planet Earth, because of course, planet Earth is our canoe. This is all we've got floating through space. The physics tells us that the energy flow through, the sun isn't changing on scales that are going to matter to us. We're sitting in the middle of this energy waterfall. This is the matter we've got. It has built this amazing natural system, this engine, which is already keeping us alive. This is our canoe. But looking after the canoe doesn't just depend on technical ability. It depends on teamwork. It depends on understanding that we have to get on with other people in our canoe, because, mutinies on planet Earth are going to be a problem. So the point here is that the place the physics gets you to, both the physics itself and the practice of physics, like how you find things out, is that physics is not about separating us from the system. There's this perception that, there's cosmology and quantum mechanics and they're kind of clean and they're separate from humans. That's not what physics tells us. Physics tells us that we are part, us individually, you right now and me, we are part of the global energy flow. Energy is flowing through us. That came from the sun. It will eventually end up out in the universe. But the stuff we are made of, unless we take a one-way trip to Mars and stay there, the stuff that we are made of will continue going round and round the Earth system. This is what we've got. This is the constraint that we've got. And so I think there's this kind of snobbery about physics, that things have to be clever, that in order to be clever they have to be separated, and it has to be things like that have swanky names. And that snobbery is holding us back. We can see it holding us. It held us back in the physics of the planet for a long time, because people wanted elegant patterns and they wanted it to be, nice and tidy from a scientific point of view. But what we've found is that the physics of complexity is the important bit, that we have to have the humility to look at the system the way it is. We're not going to re-engineer our planet. The rules of our planet are that the energy passes through and the matter goes round and round. There is an amazing system that already exists to keep us alive. And so having the humility to look at that system and see ourselves as part of it is the critical thing. We can use lots of swanky technology, but fundamentally we need to integrate that into the way the planet already works instead of trying to reinvent the engine from the ground up. And so perspective matters. And that is all I have to say. Thank you.
Thank you so much, Helen. That was absolutely fantastic. I really also enjoyed the background sound of some seagulls. It made me feel like we hadn't actually left Cornwall and we were still at the G7.
I am in Cornwall, but not at the G7.
So I wondered first if I could jump in with a question. Is obviously physics is governing all of these different aspects, but I wondered if you'd seen any direct influences of technology in your work, how technology has benefited your research over your career in science.
So there's a yes and no answer to that, because obviously technology helps you study things, right? If I can have a smaller camera that can get into those waves in a less invasive way, that is a very useful thing. Technology is also in danger of holding us back, because in the world of big data, you have so much data, and what you find is that you try to understand all the data and you miss the mechanisms because you haven't got a human looking at a breaking wave. It's easy to treat it a bit like a computer game, to be honest, to say, oh, well, I just need a model that sort of works. And that's not, you know, we need models, they're really important. But I think that the danger is that as we ocean science have always been very data poor, and satellite data and ROVs are starting to make us data rich. But the problem is, the risk is the humans stop looking at the mechanisms, and it is the mechanisms that matter. So there's a limit to what AI, to the extent to which AI can help us, because it might tell us there's a big pattern, but it doesn't tell us why the pattern is there. And it's what we need to know to understand the system is why the pattern is there. I mean, if you were going to go to a doctor and you needed some medicine, would you pick the one that says, well, last time we gave this to someone, they lived? Or would you pick the one that says, this drug is going to go to this part of your system and it's going to shunt these things around and it's going to have this outcome? And so technology does help, but it's the mechanisms that make the models, make our understanding meaningful. And so we have to be careful, I think, we can't take the human pattern recognition and mechanistic understanding out of it.
Yeah, completely fascinating answer, and it must make recruiting for your research group really complicated, because you have to find people who understand that nuance. It's not just the mathematical modelers; it's also the people who are willing to go out on these big expeditions.
Well, actually, the biggest battle is finding people who've got the character to do it. So when you're at sea, you have to muck in, and you need humility, and you can't have any ego. You need to get your science done, but everyone needs to get everything done. And actually, the biggest battle is finding people who understand both how to take individual responsibility, but how to work in a team and how to actually make the team work. And that is far harder than finding someone who can do the maths. But it's why I really like the people in ocean science, and it's because you only get asked back on the ship if you can do that. And so the nice people, the good team workers, the good colleagues to have, they get asked back, and some people don't.
It's like your astronaut point. So a good question is, a question that I'm hoping you can answer, because I definitely could not. Is the heat anomaly over Siberia serious as regards to methane release accelerating greenhouse cover?
Yes, so I actually had a slide of this and I took it out for time reasons. So the context here is that the way the planetary engine works, it mostly shifts heat from the equator towards the poles. But because of the feedbacks in the Arctic is warming much faster than the rest of the planet by quite a lot. And in Siberia, there is a lot of permafrost with frozen methane beneath it. And the permafrost matters. So there have been a lot of worries about methane seeps under the ocean. They seem not to matter as much because the methane just dissolves in the ocean and gets eaten, never gets to the surface. The permafrost being destabilized is potentially a really serious problem. So methane has a relatively short half-life in the atmosphere. It's about 7 years, whereas carbon dioxide stays for hundreds of years. But it has a really strong warming effect. So when it comes to slowing down the rate of heat flow out into space, methane is really significant. So yes, the destabilization of the permafrost is really serious. And there are two other things that make it serious. One is that it's a vast area. Remember when you flatten out a map, that the bits at the top always look a bit bigger than they are really relative to the middle. But it's that it's remote and there isn't much open data. So Russia does share scientific data, but it's not as easy to get to and to measure as other places. But yes, the destabilization of the permafrost is a really massive problem, a really massive injection of energy into a system that won't stay in that area. It will be distributed around the rest of the system. And this is all about patterns. It's not about an effect in one place. It's about you shunt the pattern. And so the patterns of weather will change. We'll still have weather, but the patterns will be different. And we rely on the patterns being as they are now.
It's so fascinating also, actually, in your answer to that, that it's not just the advances in technology and the humans asking the questions, but also transparency and data sharing. You know, we can accumulate as much data we want about planet Earth, but unless we're sharing it equally and fairly, it's really hard to learn from. Okay, we have time for one more question. If the thermohaline circulation slows, does that affect the ability of oceans to absorb carbon? I believe that pumps have been slackening since observations started.
So the context here is that that breathing process that I showed, there are some places where the water carrying the carbon that has just been breathed in is then moved down into the deep ocean. And if it's moved down there, it's moved at least for a few hundred years away from the surface. And so it's kind of taken away. And this process, it's known as carbon export. So the big question is, how, in a bigger picture, is how much of the carbon that the ocean breathes in at the surface goes down, and it's a tiny, tiny fraction. That's why iron fertilization doesn't work. All that stuff about putting iron in the ocean, it's nonsense. And the reason it's nonsense is that it generates a load of life at the surface, and then it just breathes straight back out, just goes straight back up. It's only ever a tiny fraction that even might go down, and only if it's in one of these places where that shifts downwards. So the thermohaline circulation is a bit spiky. It's not changing it's not changing fast enough to really affect these things. What is changing much, much more quickly, and that I would worry about much more, is the life in the ocean. So the carbon pump, the thing that helps take carbon from the surface down into the system. That pump depends on how healthy the surface ocean is and how many nutrients there are, and whether we're overfishing it and things like that. And it's that carbon pump that is the biggest that has the biggest consequences on how much carbon is going down. So the thermohaline circulation does have an effect, and it is spiky, and we're still understanding it. It's thought that the Gulf Stream, for example, that has slowed down a little bit, like that part of the AMOC, the Atlantic meridional overturning circulation, has slowed down a bit. But really the problem is how we deal with biology in the surface ocean. And those exchanges and having healthy ecosystems, that's what's going to change the carbon pump on the scales we need.
When a physicist says biology, I start to get really concerned, because I didn't have left biology behind a long time ago. Okay, that is absolutely all we have time for. But if you enjoyed that, I can fully recommend catching Helen's phenomenal Christmas lecture at the Royal Institution, which was all about the physics of planet Earth, and it is available on their website. So with that, I want to say thank you so much to you, Helen, for jumping in, for doing this phenomenal talk, and for introducing us all to the physics of climate and the universe and everything. So thank you so much for being here. And everyone, come back in 20 minutes for our next session, and we'll be hearing about all things, well, Helen might think it's a little too small and science heavy, but all things quantum when it comes to sensing. So thank you so much for joining us, and see you all again soon.